So today I'm going to talk about work we've been doing with the IESNA on daylight modeling, simulation, standard methods, and standards. I'm going to quickly go over why we're doing this, a brief introduction for why we're doing it. I'll go over an outline of the document that we are creating. I'll go into some details on some of those methods and standards we're starting to develop, and then I'll finish showing some of the gold standard test cases that we're creating that will be able to be used to validate software. So why we're doing this, really overall we just need more accuracy and consistency in our daylight modeling. We need, we're doing more and more annual and climate-based daylight modeling, and we really don't have a good way of validating this annual simulation. So we know lighting software is valid at point in time on electric lighting conditions, but we don't have any way to really validate the annual situation. And when we're doing these annual calculations, there's a lot of shortcuts that we take, a lot of assumptions, a lot of interpolation that happens. We're modeling, we're trying to estimate 4,400 some sun conditions, so there's a lot of shortcuts we take. The daylight metrics world needs this because we need more apples to apples comparisons. You need to be able to give a model to two different designers and get the same result. Like we heard earlier, these two examples at the top, depending on how you treat the window shade, you can get a totally different result in your credit. One lead point or no lead points. In the energy modeling world, we need a little more sophistication in our daylight modeling. We often just spread one window on an entire facade and we model these thermal zones that are an entire length of a facade, and this is how we're estimating our energy savings. So we just need more sophistication to help encourage more passive and more creative daylighting solutions. We need just better modeling in the energy modeling world. Designers, when we're starting to look at more photorealistic renderings and doing daylight glare probability, we need assurance that those are true renderings and they really represent what we might experience. And then when we're doing these glare calculations, we need to have an accurate representation of that environment to get an accurate daylight glare calc. So what we're putting together is, the working title is the Daylight Modeling and Simulation Methods and Standards, Test Cases for the Evaluation of Daylighting Analysis Software. It's really similar to the ASHRAE 140 standard. Best test, it's a standard method of test for building energy simulation computer programs. So it's similar to that, but it's for annual daylight modeling. The goal really to document all current knowledge and best practices, but also we understand there's a lot of areas of assumption, a lot of areas where we need a little bit more research that we'll see developing over the next 5 or 10 years. And so we're kind of highlighting those areas where research and field research could help inform this effort. So this is an effort by the Daylight Modeling and Simulation Task Group. We're a subgroup of the IESNA Metrics Committee. We're hoping to have an initial release of this document in early 2020. And as I said, because there's some areas of assumption where we really see this as a growing document, over the next 5 or 10 years, we'll be updating it, ultimately growing into a more static document from the IES. So here's a quick outline of the document we're putting together. After an intro and a background, we'll have a section on modeling methods and standards. And so these are the elements that go into the model, how we characterize those, what are included, all the objects that are part of a daylighting model. That's separate then from the simulation standards. So that one model can then be simulated for sufficiency. So our section 3 is standards for simulating for sufficiency. So this is annual simulation when we're just trying to predict how much light do we have. Do we have enough light? This also relates to circadian rhythm analysis or whole building energy predictions. So that's the first section, simulation for sufficiency. But then separate from that, simulation for daylight quality. And so when you're doing daylight simulation at a point in time and really trying to see glare and qualitative stuff, there's different ways we should be simulating our model, and different ways we define the model. The last section then is the gold standard test cases that we're putting together that software vendors can then use to validate their software. So just to dive into some of the standards we're looking at, one of them is trees. I think trees have a huge impact on the daylight availability in a space, but I think it's it's not very often modeled, right? The project on the lower left there was a big, huge glass facade that I was working on in plan. This is a nice exposed southern facade, but we can see this tree canopy is really impacting the daylight availability there. So we're working on standards of how can you define those tree shapes, how can you define those canopies, There's other cases where you might have a forest around your site. So how can we, model that tree horizon, or maybe it's a cityscape. And so how do you model that tree horizon? How can you map that horizon to the model boundary and get the impact on daylighting from that, but without modeling the entire planet, right? Without modeling the entire area. Another, how do we model the seasonal characteristics of some of these trees? I think it's a great passive strategy to use deciduous trees to give shading in the summer and exposure to solar in the winter. I don't know anybody who has done an annual daylight analysis with trees that drop their leaves. So that's one of the pieces that we could start addressing here. And then besides trees, how do we model other exterior geometry? So in Colorado, we have projects up in the mountains where we might have a mountain line that we, how can we translate that to our model boundary and get the right results from that? How much of the ground do we model? Here's an example of a north classroom. I was just doing a lead calculation for it, and the amount of ground that you model and how much of the building, if you model the building across the street, really will impact the results you get for that. And then moving more into the model, we'll have standards around surface materials. Historically, we've always used 20, 50, 80 as kind of common reflectances for floors, walls, ceiling. We say architectural surfaces can be treated as diffuse. And I think this is true for sufficiency analysis. I think that's absolutely true, and those numbers probably hold up. But when and where should you use a more specular definition? And when should you go to a more detailed BSDF definition, a scatter definition? And when you're using scatter definitions, when do you need to use a high resolution one versus when can you use a low resolution one? We're finding that the low resolution is sufficient for the annual sufficiency analysis, but as soon as you start doing glare analysis or starting to do qualitative analyses of these, you really do need the higher resolution, and you need the specularity in your materials and whatnot to really capture that stuff. Then beyond the modeling standards, we'll get into some of the simulation standards. There's a number of ways that we simulate an annual condition now. Daylight coefficient methods are becoming pretty prevalent and popular, but they have some downside and some error that they introduce. There's other methods using annual suns and sky bands. These can be a little more accurate as far as the sky patches, not having sky patches, but they have they have other issues as well. They can't work with dynamic elements. So we'll have guidelines around which simulation method to use and when, and the pros and cons of each. We'll get into some of the simulation settings. When you're using ray tracing or radiosity, what settings should you use to get what level of accuracy? I think right now it's kind of a shot in the dark. What is good right now is that we often do daylighting analysis in a relative way. We often have a baseline, and then we kind of look at improved designs based on that. So that helps, but it'd be good to have more relative accuracy. And then shading control simulation will be part of this as well. This is not as headed up as much by my group, but there's a lot of work in the LM83 updates going on with shading controls. So I'll finish up here with some of the test cases that we're creating. So we're creating these test cases using a validated radiance simulation engine, using under pres skies, using the best available material definitions and standards. And really these test cases are for evaluating the overall accuracy of software. So different software features, the settings the softwares can use, and any other annual calculation method. The test cases, we have a number of base geometries these test cases are being built around that just represent anywhere from a small single office anywhere to a larger open office shared space, as well as high bay spaces such as gymnasiums. Those base geometries then will have different sets of test cases ranging from simple to complex. So at the simplest level, we'll just have a simple single room, no exterior objects, that softwares can use to validate whether they can predict that. And then we get to more and more complex sets of test cases that might add these tree definitions outside, or they might add an urban environment, and they might put these rooms down in the base of an urban canyon. So we'll have various sets of test cases like that. And then we'll be running these gold standard or ground truth simulations of these test cases. And what we mean by this is we call it the annual brute force method, where we really are just simulating every hour of the year. We're using radiance parameters, very high setting radiance parameters that give less than 1% error. And so this really should give us more of a ground truth annual simulation, which we can then compare our other results against. This takes 16 days on a single core. This is why we don't do this in practice. This is why we have all these other shortcuts that we like to use. We're doing these simulations with and without window treatments to just get rid of that factor, so we have a more so that doesn't muddy up the water. But then you can still look at different shade control algorithms by combining those two, right? So you can look at with and without, and you can still do, we can still have validation for shade algorithms. The data will be provided in annual summary form, so kind of annual average, annual metrics, but also as just a metric, as a data file that has every 8/7/60 hour of the year that you can compare in in a lot more detail. So just some of the results of, this is for the small room test case, no obstructions outside. So this was our gold standard results. And these are some of the annual summary results that we think will get published. So just looking at annual average, daylight saturation, daylight autonomy. And then you can see this is a test software. So this is a software that took 9 minutes rather than 16 days. And you can see the results are fairly similar, but not quite there, not quite accurate. And then you can look at the difference. This is the error that software had. So it's interesting to note that in some of the sufficiency metrics that we use, daylight saturation, there's quite a bit of green. So that shortcut that took only 9 minutes, when we're just looking at overall sufficiency, actually worked out okay. It wasn't that large of an error. You can see the error is a little bit higher in the back of the space where we have lower light levels. But that's good news. The bad news is that there's a lot of error in some of these others that we need to be aware of. Here's a similar software that just the same software but run at higher standards or higher parameters. This one took 7 hours. You can see the results are better, although there's still some disconcerting errors that after 7 hours I'd hope my result was a little more accurate than that. So those are the test cases. Next steps, we'll be finishing up this document. We'll update some of the other IES documents with some of these results. And next steps for our colleagues, we'd like to see more modeling and simulation research and more field research on glare, just to get more accurate in all those areas. So thanks for having me.
Thank you very much, Zach.